Again, these are the last problem or two of 4.1, 4.3 max and min notes from Friday the 15th. Sorry, rather Wednesday, October 15th. And we went through a daily problem. We looked for critical points and critical points of a function and looked through extreme value theorem. Talked about what that meant. What a critical point was, an interior point, an endpoint. We looked at some examples, and then we worked through a problem where we found extreme values for a function and talked about how to decide if extreme values are going to exist through the extreme value theorem. We found critical points, which are going to be candidates for extreme values or local values. And then we plugged in those values through Wolfram, found a few output values. One of them was a global max, 2. Well, 1 is also a global min, but it happened twice, -3. And then at 0, the function value f of 0 being 1, we might get some sort of a local value. And to decide that, we used a sign chart, much like you did with velocity, acceleration, and position. And the first derivative test is telling you, because your sign switch in your derivative at 0 went from positive to negative, that meant your graph went from increasing to decreasing, went from up and to the right to down and to the right with a horizontal tangent line at 0. That means that we must have a local max in y equals 0. So then we found critical points of another function. We decided through, again, a sign chart that those critical points were values, were locations where we got local maxes and local mins. Then we left off with this problem. So I want to encourage you to try this problem and then check your work here, because in our notes we have that posted. So here's that work, and you can check your work. We got one more problem left, and let's work through that here. So we have a function, x to the third times x plus 4 on -8, 8. Find extreme values. First thing we'll do is to check to see if the extreme value theorem guarantees such values to exist. If it didn't guarantee extreme values to exist, they might still exist, but we wouldn't be guaranteed that they would. So let's take our function, and let's say our function f of x is, we know it to be cube root of x times x plus 4, and we're wondering if this is defined for all x values from -8 to 8. Is it continuous on those values? So x plus 4 is for sure continuous on -8 to 8. It's just a line, and no issue with plugging in -8 to 8, those values into x. Now, the root part, we know for square roots, 4th roots, 8th roots, that there would be 6th roots. There could be an issue with it being negative on the inside, but because it's an odd x to the 1/3 cube root of x, it's possible to have, say, -8 in there. The cube root of -8 would be -2, -2, -2. Negatives are allowed. So cube root of x also defined for -8 to 8. So this is continuous. The function is continuous on -8 to 8. Extreme value theorem guarantees. Extreme value theorem, extreme values, both a absolute max, absolute min, or global max, global min. The global max, global min are going to happen at either -8 or 8 for the endpoints, or they'll happen at critical points. We need to find critical points. Critical point process is something you've done before. You need to find your derivative, f prime, and f prime will be the derivative of x to the 1/3 times x plus 4. And you could do two things. I suppose you could do the product rule, or you could distribute and make it maybe more simple for yourself. So if we distribute first to avoid the product rule, that x is to the 3/3. So this is x to the 4/3 plus 4x to the 1/3. Now, when you take the derivative, it's termwise, and the first term becomes 4/3 x to the -1. So 1/3 plus 4/3 x to the negative 2/3. There's our derivative. And we are going to find critical points by figuring out where our derivative is 0 or doesn't exist. Before we do that, it's helpful to combine our terms into a single fraction. So 4x to the 3rd over 3 plus 4 over 3x to the 2/3. Our common denominator would be 3x to the 2/3. So let's give the first term an x to the 2/3. This makes our derivative with a common denominator 3x to the 2/3 and a 4x plus 4. Now, if that's our derivative, we have a numerator and denominator. We can more clearly see when it would be 0, when it would be not existing. To decide where the derivative doesn't exist, f prime does not exist at x equals 0, because we're looking at when the denominator could be 0. If the denominator is 0, that derivative doesn't exist. We can't have 0 in the denominator. It makes the derivative undefined. So f prime doesn't exist at x equals 0 because x equals 0 makes denominator 0. 0 is also, x equals 0 also, let me write it like this, 0 is in our interval -8 to 8. So two things. One, it's in the domain we're talking about. Two, it makes your derivative not exist. 0 is a critical point of function f. It's possible there's another critical point of function f, and to find any other critical points, we consider when our derivative is 0. Derivative was x plus 4 over, so that's x plus 4 over 3x to the 2/3. If this fraction, if this derivative is ever 0, it will be because of the numerator, not the denominator. So consider the numerator. 0 equals x plus 4. That happens when x equals -4. So numerator and f prime. Now let me say this. Numerator is 0 at x equals -4. So f prime at -4 also 0. We would get a horizontal tangent line at -4. Again, -4 is -4 is in the interval -8 to 8. -4 is a critical point of function f. So we have 4 locations to check. We have the 2 critical points, -1, -1 there, and then 0, and then we have the 2 endpoints, -8 and 8. To decide if you get absolute max and absolute min at these locations, you have to plug them into the original function and see what you get. So first factor, cube root of x. If we plug in a -8, we get -2. If we plug in a -1, we get -1. So -2, -1, we get 0, and we get 2. Now, plug those same inputs into x plus 4, and we get -4, we get 3, we get 4, and we get 12. -4, yeah. So we're going to get an 8 and a -3 and a 0 and a 24. Okay, so 24 is the global max happening at location 8, endpoint 8, and then -3 is your global min happening at critical point -1. At the others, let's see, 8 here is a value and it happens at an endpoint. This, because it's at an endpoint, neither can't be a local, I should say, cannot be a local. Since -8 is an endpoint, since -8 is an endpoint. And then, but at 0, we might get, could be a local. To decide, we need to look at a sign chart. I'm going to pause and then build a sign chart. Okay, I'm recording again. Okay, here is our number line. And at location 0, that's what we're considering could be a local value, local min, local max. Our derivative was 0. We have a horizontal tan line. And we need to look at the sign before 0 and the sign of the derivative after 0. At -1, we already know what it is. At -1, it's -3. And so at -1, it's -3. So we have negatives on that interval. If we weren't convinced about -1, we could do -0.5, but it would still be negative. We'd get a negative from our cube root, and we'd get a positive here. It'd still be negative. Negative, I don't know why I wrote positives. So negative, 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 negative. Okay, our graph is decreasing there. And then if we plug in a 1 to our derivative, f prime 1, then we'd have cube root of 1, 1 plus 4. This is all positive. So plus, 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 plus. Graph increases. We do get a local min at 0. And that's f of 0, which actually turns out to be zeros. Lots of zeros. Let's see. I'm going to pause again, and then let's pull up that graph and just and see what's going on. Okay, let's finish with the graph, and then I need to go back and mention I made a mistake. We're wanting the sign chart for the derivative, and I'm plugging in test values to find the sign, but I plugged them in here to the function. The derivative was not cube root in x plus 4. Derivative was f prime was x plus 4 over, and it was 3x to the 2/3. 3x to the 2/3. So if we tested, let's see, our signs. If we tested a -1, f prime at -1, we're going to get a positive 3 in the numerator, so plus, and then the negative in the denominator gets squared there, so it's plus. We're still plus. Oh, we're plus there, plus, 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 and oh, you know what? We're testing the wrong thing. I realize now. We can't have a local because the derivative didn't exist. Let's go back because this isn't working either. As we approach 0, derivative is positive, and then let's try f prime at 1. And again, it's going to be positive and positive, plus, 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 plus. So there's no switch in sign. The graph increases and increases, and we can see that in our picture. The graph, as we approach 0, here's 0. As we approach 0, the derivative has positive slopes, and then it stays positively sloped. Here, f prime is positive. Here, f prime's positive. There's no switch in sign. There's no local. And I suppose we should have known that. We can't have a local because the derivative didn't exist there. Okay, and with the picture, what is it telling you? We had, so on -8 to 8, f of 8 is 24, and that would be somewhere up here, because after our vertical tangent line, the graph increases without bound, and so over at -8, we'd be at a height of 24, and it would be our global max. And then at -1, we get our -1. We get our -3. There was our global min. All right, y'all take care. Reach out if you need.